Hello, welcome to this presentation introducing the basics of electrocardiogram monitoring. Specifically in this presentation, I'm going to talk about how the conduction system of the heart works and how that's going to show up on an ECG tracing or on that paper strip that comes spitting out of the machine. This is not for necessarily a 12 lead, although it works for that. I'm going to concentrate mostly on what it's going to look like on a telemetry monitor or something that has a continual ECG feed. So to start with, the electrical conduction of the heart, you have to think of it as a wave moving through the myocardium. It's going to start with the negative side and move to the positive side, and that's the top to the bottom. And most of the time when you look at the tracing, it's going to be set up on this type of a view, so you can see this wave either moving away from you or towards you or going to side. Think of it like if you were standing on the beach looking at the ocean and the waves are coming towards you, then that would be the opposite of what it normally looks like when you look at the ECG. The ECG normally looks like if you were out in the ocean and the waves are moving towards the beach. So that's what's happening in the heart. Just a quick review of what this looks like inside the heart itself. This is a cross-section of the heart. You can see all the major anatomical markers. You can see up there in the upper left, that's the SA node. That's where we really want the impulse to begin. And when we get talking about the problems of the heart, that gets messed up, and so the impulse may start from a different place. But normally, that's where we want the impulse to begin. And it jumps across that right atrium really quickly, lands on that atrioventricular node, and then it sends it through the ventricle and terminates out in those little Purkinje fibers in the left atrium and the left ventricle and right ventricle. So again, this is a wave of depolarization, and depolarization is followed by a period of time that's called repolarization. Now, the SA node is the heart's dominant pacemaker. We showed you that in the picture before, and that's where we really want that impulse to begin. If it begins there, then we're going to call whatever is happening a sinus rhythm. It must begin there if it's called a sinus rhythm. If it's not beginning there, it can't be called a sinus rhythm. That's going to come in handy when we start looking at the different types of problems with the heart and its conduction system. Each depolarization through the SA node spreads through the atria, producing a P wave. And we'll show that on the ECG strips in a later video. Beginning, we're just going to look at these as we go. But remember that first little bump you're going to see on the ECG strip is the wave going from the SA node to the AV node. That is the P wave, or atrial depolarization. We hope that's happening. It doesn't mean that it for sure is, but with that movement of electrical activity through the atria, it's going to show up that P wave. Once it gets to the AV node, then we're going to see that beginning of the ventricles contracting, and we'll see that when we look at the full wave of depolarization on the ECG strip. Now, when that electrical activity hits that AV node, there is a slight pause. We don't really see it very much on the ECG strip, but it is briefly noted there, and I'll show you when we get to the picture of that. Now, when we look at an ECG, we talk about waves and complexes and intervals. And anyway, we're going to take each of these pieces one by one and explain them so you understand what each of them are and what they represent. So the P wave, as I mentioned, is that atrial contraction. The QRS complex is the ventricles contracting. The T wave is when the ventricles repolarize. And sometimes you're going to see a little U wave hanging out there at the end of the T wave, and that's the repolarization of the Purkinje fibers. It's not always there, only under special circumstances. Now, intervals. These are really important when we start talking about different types of dysrhythmias because the intervals get longer, shorter, or mixed up. So the PR interval, this is where the atria have a brief pause before that ventricular activity can happen, before that AV node gets the message. The ST segment, this is the early part of the ventricular polarization because, as you know, with that heart, the atria are small in comparison to the ventricles. So the ventricles are going to take a little bit longer time for that wave of depolarization to get through the whole muscle. So if you think again of a big long segment, it starts to depolarize and it moves along, and we're going to see it in different, on the ECG, different portions of that big long wave depolarization. The QT interval is where the ventricular depolarization and the repolarization start to occur. So immediately as it depolarizes, it wants to repolarize again. So at one given time, you're going to have a segment repolarizing as well as a segment that is depolarizing. The TP interval, there's no electrical activity happening at that time. The P to P interval is representing the atrial rate and rhythm. So that's saying the atria contract here, and then down the way a little bit further, you can see another P wave. The distance between those two P waves is the PP interval, and that's really indicating one atrial contraction to another. The RR interval is the same thing, only it's related to the ventricles, their rhythm and rate. Now this is going to show up on this funky little paper that's in a graph shape. And it's important to know what those little boxes represent. So across the bottom, this is going to be time. And as it spits it out of the machine, it's going to just keep feeding it out, kind of like a receipt from the store. And that's the time period as it gets longer from left to right. That's the time. The voltage is how much amplitude that electricity is being measured on the paper. Now you look at these boxes and you're going to see that the voltage goes up in millimeters and the bottom is in seconds. So if you see a big box, then that is 0.2 of a second. The little boxes are 0.04 of a second. So you can see that it's a pretty small amount of time measured. We can really get it down to a small portion of a second. This is an actual single beat. Now you can't really see it very well because of the particular dark lines here, but you can see if I move my cursor up here, this is the beginning of that P wave. And this is a big dark box. So that right there, you can see if we kind of figure it out a little bit here, that these intervals and distances can be measured using these little boxes. So the whole P wave itself is 0.11 of a second. The PR interval we measure from the beginning of the upslope right here to the beginning of the next upslope. So this here is the PR interval. And the normal range here is 0.12 to 0.2. And as you can see, we're just short of that 0.2 because if this distance between this dark line right here and this dark line right here is 0.2, we're just a little bit short of that because we're a little bit in here, a little bit in here, so we're within the normal range. QRS complex, again, is that measured from the first up to when it's back to that isoelectric line, and I haven't mentioned that yet, but we'll get to it. ST segment is that period from this T wave right here, or the S wave here, to the T wave that begins as the upslope there. It's a long bump there. Remember that was when the ventricles are repolarizing, and the U wave, if it's that present, is back there at the end. The whole QT interval is measured there. So depolarization shoots rapidly through or from that AV node through the bundle of His and left and right bundle branches. This is a quick impulse, and we see it showing up as that big up motion here and then down. That is a big fast wave as it depolarizes, and it's very quick. The bundle of His and the both bundle branches on both sides, left and right ventricles, repolarize as they begin to depolarize, and that shows up mostly in that T wave. Like mentioned here in the slide, that whole process of depolarization is represented in the QRS complex, and the Q wave, when it's there, always occurs at the beginning of the QRS complex, and there might be a little tiny downward deflection if you see it. Otherwise, it's kind of hidden in that upward deflection representing the R wave. The next downward part is the F wave. Showed you that before, and the horizontal segment of the baseline that follows that QRS is known as the ST segment. I showed you that. If the ST segment is elevated or depressed below that baseline level, this could be a sign of problems. We'll catch you up to date on those when we get to the dysrhythmias and problems. The ST segment represents the initial phase of that ventricular repolarization. As I mentioned before, as that wave goes along, it's going to start to repolarize before it gets done depolarizing. The T wave is that final little bump that I showed you, and that is generally a broad hump, and it represents ventricular repolarization. So you can see it here, what's happening as far as depolarizing and repolarizing. So here you have the P wave, the atrial depolarizing. We hope that that's indicative of contraction. Then it hits that AV node. There's a slight pause here. Then the ventricular contraction occurs, a wave of depolarization there. Again, another little pause, and then they repolarize. So the question is then, if we see the ventricular depolarization and repolarization, why don't we see the atria repolarizing? What wave is that? And the answer to that is a little bit of a trick, because where would it occur? If you're thinking of this line, where would it occur? That's right in this area here. And we can't see it because this massive amount of myocardial muscle is depolarizing, and it hides whatever would be showing up from the atria. So it's hidden. This is a color graphic of what I just explained, and it's maybe a little bit easier to see what each thing represents. So I'll have you take a look at that, examine this diagram, see what you think. If you need longer, hit pause. We're going to move on. Repolarization is accomplished really, if you think physiologically, the potassium ions are leaving the myocytes, or those muscle cells. The ventricular systole, or the contraction, begins with the QRS complex and continues until the end of the T wave. So physiologically speaking, a cardiac cycle represents from the atrial contraction and ventricular contraction followed by a little bit of a resting period. So that's the entire cardiac cycle. Now there's a refractory period, and that refractory stays right after depolarization. So before it can depolarize again, it has to begin that process. The absolute refractory period is when the cell cannot fire off other impulse. It cannot switch those ions around. There's no way it can happen. There's zero excitability. The relative refractory period it's possible, but it's difficult. It's the action potential. It takes more of an impulse in order for that to fire, and so it's possible to do it, but you're not going to get a really great wave of depolarization. And on the ECG, from the mid T wave to the end of the T wave, that's where this is. So in order to illustrate this a little bit better, I use this analogy of a toilet. Everyone knows about a toilet. You've used one before, and so you understand this analogy because you're familiar with a toilet. So the absolute refractory period is when you flush the toilet, and if you want to flush it again, if you hurry and push the handle down again, nothing's going to happen because there's no water filled up in the tank yet. So you might sit there and push that handle up and down, but there's not enough water in the tank to make another flush. So relative to the heart in the cells, there's no way that they can send off another impulse because they just can't, they won't do it no matter how much the stimulus is. Now the relative refractory period is similar, but if we go back to that toilet analogy, you're standing there and if you wait just a little while, a little bit of water fills up into the tank. So you push the handle down and it kind of flushes, it gurgles and swirls around a little bit, but it's not a real flush. So in terms of the cardiac cells, the electrical impulse may be able to fire, but it's just not going to be very significant. So that really is the foundation of what happens in the heart and the beginnings of how you can interpret an ECG. So I hope that helped. Go on to the next video available that will show you more about ECG interpretation. If you liked this and you found it helpful, go ahead and click or leave a comment, or hey, even do both. Thanks for watching.